We're going to keep on going in chapter 5, and this time we're going to move on to the definite integral. So first off, what did we learn before? So what we learned before is that you can approximate the area under a curve by using the summation, where the summation talks about, as n goes towards infinity, and n is the number of rectangles that we're looking at. So as you get more and more rectangles, then that is the approximation of your area. So that's what we learned in section 5.1, is that the area under a curve could be approximated by the summation from I equals 1 to n of your function value approximated or plugged in some sort of x value in the interval times your delta x. And if you do more and more rectangles, so more and more subintervals, then that gives you the area. So using that, we can define what a definite integral is. So a definite integral is actually the same as the area under a curve. So here's your, official definition, is that the integral is equal to the area under a curve, which is equal to the limit as n approaches infinity of the summation. Now, as far as how we're going to read this, we read this as the integral from A to B. So A tells you that left-handed endpoint, B tells you that right-handed endpoint. So the integral from A to B of f of x. Really important that you have this dx here. I'll talk more about that in just a minute, but this is the integral from A to B of f of x. And that's equal to the area under a curve, which is equal to adding up all the rectangles, but allowing the number of rectangles to go towards infinity. And that's what this second portion is, and that's what we worked with in 5.1. If this limit exists, then we say that the function is integrable on the interval from A to B. So a lot of new definitions here. It's almost like we're not in a math class, we're in an English class, but the integral from A to B of f of x is equal to the area under the curve, which is equal to the summation of all of those rectangles as the number of rectangles goes towards infinity. Now, as far as what these xi's are, the xi's can be any x that was in that subinterval. It's probably smarter to have some sort of method to how you choose those x's, but it could be any x that you want. And if you can find this limit, we say that the function is integrable on the interval from A to B. A little quick thing about the integrand or the integral sign. You'll see it used both ways. It was created by Leibniz. So it's called an integral sign, also called an integrand. So you can see here again, it's called the integrand. It's the limits of the integration, lower limit A, upper limit B. If you're thinking about what those are, it was on the x-axis. So it was from left to right. So A is always on the left, B is always on the right. dx, we don't say it. When I read this, it's actually an entire sentence. I say the integral from A to B of f of x. Right? I wouldn't say the dx, but it's really important. And it's really important because it tells you what the variable is. This dx says that A and B are coming from your x-axis. If I say dy, that's different, right? I'm talking about my A and B come from the y-axis. So it's really important that you put the dx there. It's also the same way, if you remember whenever you learn differentiation, I learned that the derivative of x to the n is nx to the n minus 1. But it's important that I put dx here because that told me that x was the variable. So the same reason I put dx on the bottom with differentiation, I have to put a dx at the end for an integrand. Otherwise, it doesn't make any sense. It doesn't tell you what's the variable, it doesn't tell you what axis you're splitting up, nothing. So you've got to put that dx at the end. The process of all this is called integration. So the definite integral, it is a number, and it does not depend on what x you choose. So if you think about this, I said before that xi star, it doesn't matter where you got those x's, so you might as well just use one of the sums that we've done before, either the left or the right. Those are called Riemann sums. So German mathematician Bernard Riemann. Also, variables don't matter too much. These are all equivalent. All of these integrals are equivalent here. As long as you have the same variable on the inside and the d, that variable, then they all mean the same thing. So what we're doing is we are going to be looking for Riemann sums to approximate definite integrals. So that's what we're doing here. Again, it doesn't matter what x you choose from those subintervals. I mean, if you're looking at this picture, it doesn't matter which x sub I I'm choosing, left or right. But what is customary is it's kind of customary to choose the right, which I think we'll say in just a minute definitely. But just so you know, we are going to be usually using the right-hand side. As far as a picture goes, this is your picture. We're looking at the area under a curve. Same picture we were looking at before. It's just now we're representing it with an integral instead of a summation. As far as integrals go, we're talking about area. The area is calculated from the x-axis up towards the curve. If your curve falls below the x-axis, that's negative area. So when we talk about an integral, we're adding up all of the area. Some of that area could be negative. So area above the x-axis, that's all positive. So all of this, that's all positive. Area below, that's negative. So area below the x-axis is going to be negative. Just keep that in mind. If you start computing areas and you have something that is below the x-axis, make sure that shows up as negative. And if you think about it, assuming that you're doing it the right way in terms of the formula, you should get negative values. Because if something falls below the x-axis and I'm computing f of that value, I should get something that's negative because you'll get a negative y value. So just make sure if the area is below the x-axis, it's actually negative area. So like I said before, I mean, you can read through all this, but we're using the sums to approximate the area. What we were doing is we were saying, well, the more and more rectangles you have, the better the approximation. If you let n go towards infinity, then you have the area. Well, another way of saying that is what if you make the rectangle skinnier? And if you think about the area that we did before, I had this and I broke it down into infinitely many rectangles. That's exactly the same as saying the width of these rectangles goes towards 0. You just get thinner and thinner rectangles. So saying infinitely many rectangles is exactly the same as saying the width of each rectangle goes towards 0. And that's just a slightly different definition that's equivalent. It's all talking about the definite integral. So either you can say the limit as n approaches n approaches infinity, or because we do like to have everything in terms of x, you can say it's the delta x goes to 0. So the width goes to 0. So one thing though, how do you know if something is integrable? Well, you need to have only a finite number of jump discontinuities in order for it to be integrable. And that's what this theorem 3 says. So if you want this definite integral to exist, then you can only have a finite number of jump discontinuities. So what do I mean by that? I mean something like, let's say I have a vertical asymptote here. Here's my A, here's my B. This function is not integrable because how are you going to do the area under something that goes off towards infinity right here? Right, that doesn't make any sense. So I need a finite number of jumps. So I could do something like this, like maybe my graph looks like this from A to B. That's fine. I can figure out the area under that curve. But you can't have, a bunch of infinite discontinuities. I can't have holes in the graph that are, bigger than just a point, that kind of stuff. So as long as you have a finite number of jump discontinuities, then we can figure out the definite integral. This is what I was saying before. If you're allowed to choose any x value, then you might as well just decide which one we're going to use now and just use it. And so that's what this is. Most often you're just going to use the right endpoint. It makes the most sense, so you might as well use it. So final kind of definition here. the definite integral is going to be equal to the right Riemann sum. So this is the right Riemann, I think it's R. I might have the E and the I mixed up here. So it's the right Riemann sum. And what I mean by that is when you break those subintervals down, choose the point that's on the right, plug it into your function, and that'll give you the height. So this is probably the most important slide we've had so far. The definite integral, the area under the curve, is equal to the limit as n approaches infinity of your right Riemann sum. Quick example here. Could we express this right Riemann sum in terms of an integral? So a couple things. I know my a and my b automatically because I know the interval. The interval goes from 0 to pi, that's your a and your b. So when I go to write my integral, I know I'm going to go from 0 to pi. Next thing, if you remember the way the integral is set up, the integral was set up from I equals 1 to n, f of x sub I delta x. So here's your delta x, which means that this is giving you your f of x sub I. So that means that my f of x looks like you're cubing your x, then plus x times sine x. So there's your f of x. My integral is going to be f of x dx. So I'll plug in that f of x, and that's my integral.